In this lecture, we will be studying the concept of sequence convergence. So recall the definition of a sequence. It's an ordered list of real numbers. We often denote it by a sub n. And so just think again as a list, a1, a2, a3, a4, so on and so forth. And the question we now have is, as you look at your list, and as you go further and further down the list, what does it mean for those numbers to be converging to something, to converge to a limit? And we use the following definition. We say the sequence a sub n converges to the limit L, written as the limit as n goes to infinity of a sub n equals L, provided that an can be made as close to L as we please by choosing sufficiently large n. Put another way, given any epsilon greater than 0, there exists an integer capital N such that a sub n minus L in absolute value is less than epsilon for all little n bigger than or equal to capital N. So this definition is a bit of a mouthful. There's a lot here. These two sentences say the same thing. So here you can think of this as the prose version of what it means for a limit of a sequence to exist and equal L. This is the precise mathematical definition of that. So your intuition, what this definition does is it ties your intuition of what it means that as you go down this list, you're getting arbitrarily close to some value, and it makes it mathematically precise. So we're going to dig into this, and the things to remember are, first, epsilon we want to think of as our error tolerance. And capital N is how far we must go down the list to get our a sub n beyond that nth term, capital nth term, to be within this error tolerance of L. So the way you can think of this is you're given an error tolerance and you want the terms in your sequence to be within epsilon of L. So think of this as the distance. The distance between a sub n and L is smaller than epsilon once you're past this capital N in the list, once you're far enough down the list. This defines the limit of the sequence being L, particularly because this will work for any epsilon. Think of epsilon as some tiny error tolerance. If you give me a tiny error tolerance, I can say you just have to go far enough down the list so that a sub n is within epsilon of L. And this works for any epsilon. And the idea is as you shrink epsilon, this n will get larger. If you want to get closer, if you want to get your a sub n's closer to L, you have to go further down the list. This is more naturally understood if we actually look at the picture. So this is just that second statement from the definition. And let's think about graphically what this could mean. So we had said epsilon is our error tolerance. And let's think about, suppose this is our L. So this L is actually the limit itself. Epsilon being an error tolerance, let's think about drawing this band. This would be L plus epsilon and L minus epsilon. As we go down this n axis, if the a sub n minus L in absolute value is less than epsilon, again, think of this as the distance pictured here, the vertical distance. For any n, it would be the difference between a sub n and the limit L. If that distance between these two values is smaller than epsilon, that's another way of saying you have to be within this band. So again, graphically, this means a sub n is inside this blue band. So the way we've drawn it. So let's start drawing our sequence. So suppose here's your A1 and here's your A2. And A3. So on and so forth. Now intuitively, if we think of this as the limit, and that's really what we're depicting here, the limit as n goes to infinity of a sub n being equal to this L. By definition, for the limit as n goes to infinity of a sub n to equal L, as we march down to the right, these points should be getting arbitrarily closer and closer to the line y equals L. And mathematically what that means, according to this definition, is at some index value capital N, this graph of points will enter the blue band and never leave thereafter. So maybe we're looking something like this, and then at this nth term it enters and never leaves. And this is the definition of sequence convergence, because now the way you want to think of this is, what if we shrunk that epsilon and made this band even thinner? If the limit, in fact, of a sub n equals L, what that will mean is this n will have to move to the right. And the more and more you shrink the width of this band, meaning the more and more you decrease epsilon in size, all you have to do is shift n to the right, but it will always work. And if that's the case, if for any epsilon, for any blue band, we can find an n such that from that point on, the sequence points will always be within the blue band, then that is the definition of the sequence a sub n converging to L. Now, that being said, oftentimes when we work with limits of sequences, we borrow what we know from our introductory calculus course. And if we come back to the case where a sub n is equal to a function f evaluated at n, starting at some point, usually this would be at the beginning, n equals 1 or n equals 0. But as long as at some point, so if this is your, maybe we want to say, So suppose that we have this function that has the limit as x goes to infinity of f of x being L. So this is actually a horizontal asymptote. So y equals L is a horizontal asymptote of the function f of x as x goes to infinity if the way your sequence is defined is that at these integer index values, your sequence is actually on the function. Then what this theorem is saying is that if f of x is approaching L as x goes to infinity, you have this horizontal asymptote, then these terms from the sequence are along for the ride. One way I like to think of this is kind of like saying this graph of this function is a road. And the road is going to some destination. But travelers on that road, as long as they stay on the road, have to go to the same destination. So because of this, all of the limit laws that you learned when you first studied limits of functions as x goes to infinity in single variable calculus are now fair game. And so because of that, in a lot of limit computations, we are not necessarily working with this formal definition. We're working with the limit laws that we learned in our first calculus course. But this definition is what underlies everything for sequence convergence. And what's really nice about this definition is that it syncs up to your intuition. Our intuition for the limit as n goes to infinity of a sub n being equal to L, the idea that the terms in the sequence get arbitrarily close to L, is the right one. This captures that correctly mathematically. And we will explore some more of this, how you actually use this, and this theorem, how you actually do these types of limit computations in our next lecture.